Thank you very much, Anny, and thank you very much for the invitation to be here. I think sea level is really a very exciting subject, as you have seen already in the first presentations here today and in the ones that follow. And personally, in fact, I get more and more intrigued about the paleo aspects of sea level. There's really very exciting results still to be expected, I think. What I will focus on now is, in fact, regional variability as opposed to global average sea level variability. And I would like to, I guess, to some extent recall what was mentioned before. I think in terms of really looking into the climate change and what are the most impacting parameters, of course, we can talk about precipitation, flooding, as we have right now in Germany, droughts, which would impact a lot our, I guess, food supply. But in terms of security, coastal security, security of megacities, sea level is really one of the parameters that, first of all, has a very big impact. And the other thing to note, to recall, and I think we will see this here over the next 2 days, sea level is not just the ocean. We basically often think sea level being the upper boundary condition of a volume of water, which is true, but it's really collecting information from essentially all climate components, at least the natural or the climate impacted part of sea level. And so it's really a very integrating climate component that has a lot of information about climate change, but that also requires a lot of information from the ice, from the terrestrial hydrology, from many parts of the climate system. And of course, the impacts of sea level to humans, and I will show this in the next slides, is not just global sea level. Of course, it's the sea level change that happened at the coastline. And at the coastlines, I think it's important to recall, I'm not going to address this here in details, but the later talks will do this. Sea level change is not just climate related. In fact, we see in some regions sea level change being anthropogenically induced, not climate related, that in fact might be much bigger than the climate part, and we really have to start to distinguish these two, in fact put them into relation and context. Maybe the last point, Anny alluded to this already, analyses of sea level change, sea level are very much data-based. Without data, we cannot do much. They are also very much modeling and theory-based, and you have to bring this all together to understand sea level change in the past, presently, and in the future. And I cannot address all these subjects here, but I'm pretty sure that all talks together, you basically will see this point here. Now, just to recall, Anny showed this already, this is the sea level increase, the global sea level increase curve since 1900. Essentially, Anny Cazenave showed you this part, which is the only one that is really observed in the sense of a global observations. Everything else here has to be reconstructed from an incomplete database. But I think, and this is what also has been stated already, we can estimate changes or increases in sea level. There are two rates, if you want. So one is about 2 millimeters per year if you take the entire period. If you go just in the most recent part, that is the well-observed part by satellites, you get something like 3 millimeters per year. Of course, there is a danger. Every short part might, in fact, have higher frequency variability on top. So, in concluding from just a shorter period about a long-term change is always dangerous, but this is the best we can do right now. And during this period in particular, of course, we can sort of split the contributions as Anny sort of finished her contributions. This is roughly in agreement with Anny, numbers, not exactly, where basically we can say about 30 to 40% comes from warming, something like 55 or so percent from mass addition. And that's already a shift of understanding, because in the past we assumed that a lot of the sea level increase comes basically from ocean warming. We see already that the mass addition, the melting or the removal of mass from the cryosphere has a big impact on global sea level, of course, the terrestrial hydrology, the storage of water, pumping out groundwater, and so forth, has to be included here. But it's really the regional changes in sea level, as I said already, that affect humans, the society, and you basically see here all the tide gauges where we have measurements. Some are over a short period, some are over longer periods. Here you see again the reconstructions of sea level with spread getting into a more secure region. And now looking at least two or several of the tide gauges, you start to see that it's locally, sea level change is not just smooth. There's a lot of variability here, as you can see from various tide gauges, various locations, the Baltic, and in fact some are rising, some are more flat like the Baltic. And so this indicates already climate change is not just a smooth curve increasing. There is a lot of processes involved, a lot of variability resulting from these processes. And of course, we have to understand these processes if we also want to come to accurate predictions. Just as a reminder, within 1 meter above sea level, there is many people, there's a lot of wealth. And so as one of the motivations why we really want to know how sea level is changing over the next 100 and 300 years, it's really where we are and we will be very much impacted as a society. Now, if we want to understand all these changes and from there on come to better predictions of sea level, if we in fact can understand if we can predict sea level, of course we have to look into all the processes contributing. And this is an attempt to summarize these processes. Some of them I would call dynamic, so a varying system where the forcing is varying. Some of them I would call static, where basically you have an immediate or longer term response, but there is not a lot of wobbling involved. And so in particular in this middle part, these dynamic changes are not immediately impacting the global mean. There might be some residual leaking into this, like Anny alluded to, like water vapor exchanges, other small exchanges, ENSO event, if you see this in the global mean. But for regional changes, it's particular here where basically you change the surface forcing. What you see here is the ocean basin as the Pacific, the Atlantic, or even globally, which is driven by wind stress, which is driven by the changing atmosphere. There's heat fluxes involved. In fact, there's precipitation involved. There are many other things involved. And in fact, to some extent, the melting of ice masses do put more fresh water into the ocean, which dilutes density, which in fact has an impact on the circulation. And we have to understand all these processes. But there are other processes, and these are in particular indicated here by these relative or absolute sea level change. And these differences are quite interesting because absolute, basically we measure from a satellite, for instance, relative to a reference ellipsoid or a total reference frame, where basically the global sea level is going up and down, but relative sea level is really measured sea level relative to the bottom. And that can be the coastline, in particular close to the coast. If your coastline is going up and down while the global mean sea level is being static, you would still see sea level change at your dike. And in some regions, mind you, in Tokyo, this is maybe not a very hard number, but roughly in order of magnitude, Tokyo as a city went down about 5 meters by sucking out groundwater. And so this tells you how much, in fact, we as humans influence, in particular this part, sediment compaction. If we put dams in the rivers, there's not sediment coming out. This has an impact on local sea level as well. So there are many processes, and of course, the smaller the time and space scale gets, the more we need to understand all these processes. While on a global average, the wind stress, for instance, wouldn't make much. Changes in salinity wouldn't make a big impact. A small maybe. But you basically see the more we get into regional it changes, the more we need to understand these, in particular the dynamical part, the changing part that is not static in time or just increasing. Just as an example, here are just a few tide gauges. In fact, these are 7 if you want. Some are in the more the European part, some are in the US part and other parts. And essentially these are tide gauge measurements, the raw tide gauge measurements. And if you just look at them, this is in Sweden, Copenhagen is flat, Stavanger is in Norway, pretty flat, but in particular Sweden goes extremely down. While then you have the US tide gauges, they tend to go up, but not at the same rate. And so what we have heard about the paleo information, the rebound from the last glacier ice sheets, or the melting of those, applying these so-called GRA, the glacial isostatic adjustment corrections, to these tide gauges, you start to see, okay, we are getting them now closer together, but there's still differences. Basically, some are still rising very much, some are still kind of going down. And so if people start to put now GPS measures at these tide gauges to measure the actual lifting up or sinking down of the land at the tide gauge station, which is not just the GIA correction. So you need to add an extra correction, and once you do so, you basically see this last column where now they all get into this 1.7, 1.6, 1.9 millimeter per range increase after applying all these corrections. And some of them, Galveston, is increasing very much. In fact, even after the GIA corrections, it's increasing very much. This is in Gulf of Mexico, where there's a lot of oil mining. So that's one example, for instance, where we suck out resources out of the ground, which means that the ground is responding, going down more than average. While this one here is in Sweden, where we still have a very strong uplift from the melting of the last glacier sitting over Scandinavia. And the GI correction seems to do a good job, but apparently not a totally good job, because if you put the GPS corrections on top and do the corrections, you correct, in fact, much more into what seems to be a global sea level increase. And on top, of course, you see still a lot of variability. And so what is this? And in fact, as you will see, there's a lot of natural variability in sea level affecting coastal regions as well as a global average. And so we have to understand where this comes from and how it, in fact, impacts our estimates of sea level. So coming to regional pattern, Anny Cazenave already showed these. Essentially, you see here 2 periods. One is a longer one. It's 93 through 2010. If you go over a shorter period, only to 2001, you basically see already, and after, I think this actually has a global mean removed, you see stronger variations, substantially stronger variations. You also see there are some regions that uplift very much, while others, in fact, go down. Even here, there are regions that stay neutral, or in fact go down. And this is already alluding to the fact that if you now look into longer, these what we call reconstructions, going back, in fact, to 1960, and you plot here the trends estimated from the altimeter period, 93 through 2009, and then you go backwards, 1980 to 2009, 70, 60, you start to see it's not one pattern. In fact, it goes up and down, it goes up and down. And so we started to look into these. In fact, there's a reduction in some regions, some more, some less. There's a above mean increase. And so there you see this kind of pulsation, in particular in the Western Pacific, indicating to you already there is a lot of what we call modal variability related to what we call climate modes. So in each basin, or even on the larger scale, we have climate modes where essentially the system oscillates by itself without anthropogenic impact. The climate system is oscillating. We have, for instance, ENSO is probably known to all of you, the southern oscillation in the Pacific leading to El Niño, La Niña. We have Pacific decadal oscillations. we have the Indian Ocean dipole mode, we have the North Atlantic oscillation, the Southern Ocean annual mode. Telling you that there is a lot of natural variability that, in fact, I probably can stop here already by saying that a lot of these changes that also Anny showed on the regional basis, what we see today is in fact natural climate modes superimposed to a much smaller global increase. And if we want to understand sea level change, in particular regional sea level change today and in the future, we really need to understand these climate modes. So this is again these changes I showed you before, and now compared relative to thermal temperature-induced increase in sea level from two data sets. This is Dominguez et al. And Levitus et al. For the same period. And over the most recent area, you start to see quite intriguing agreements between these two. But the more you go backwards, that agreement disappears. One reason is, of course, that the database gets weaker and weaker the more we go back. Of course, there are other regions, and to sort of anticipate these already, it's not just temperature. Salinity, in particular for regional patterns, does play a big role, and of course, we need to take salinity changes into this context as well. And this is indicated here. The period considered, this is by Durack and Weifels, a work in preparation where basically the last 50, 60 years are being considered. This is what we call steric, the total contribution to sea level, now split into thermal and halosteric part. And this is, for instance, for the Atlantic, where just from the color, by eyeballing, you can tell that the steric part is in fact smaller than what thermal would tell you, because the salinity changes are pumping against. So if you would just take temperature, often it would in fact inflate the sea level change that should result to it, because the salinity part, the halosteric part, is contributing and sometimes in fact counterbalancing the thermal part. In some regions like the Arctic, in fact the salinity contribution is dominating the change. So we have to take both into account. And of course, we have to also look into really the regional changes, the variability. And this is now coming back or getting in more into the details of reconstructions, where we basically, as a community, going back in time, trying to use all the information we have about sea level change. And what you see here is a work from Becker et al. 2012, looking into the Western tropical Pacific. It's a global analysis, but this is just the sort of zooming into the Western tropical Pacific and comparing the reconstructions, sort of taking all the information we have, trying to reconstruct sea level change over the last many years. It goes back to 1950. In black are the reconstructions, in red are the tide gauges, and then in blue is the information we have from altimetry. And you start to see, okay, at least at the points where we have tide gauge information, in fact, information that went into the estimate, we see consistency, which it should, because to some extent these reconstructions are driven by the tide gauge data. But it's very encouraging, and it allows us to construct pattern of sea level change over these longer periods. It also allows us to understand, to at least attempt to understand how sea level change is going. And you see already from this figure, it's not just a smooth increase. There's a lot of variability, but there is a lot of long-term changes superimposed. And this is work from the Indian Niddesh et al., Indians and others, where the group really looked into how does sea level change look like in these boxes, but also essentially you see here by these numbers, these are individual tide gauges. And essentially from this you basically see over the last 50 years, there is a lot of decadal variability superimposed on higher frequency oscillations and of course superimposed on the longer term trends. And these decadal variabilities can be very big. You basically see here they are in the 5 to 10 centimeter range. Again, sea level is not just a smooth increase. There is a very much increase and decrease. And then, of course, you have the higher frequency changes here, interannual variation. variability with even much bigger increase than you basically see on the decadal timescales. And so for us as oceanographers, as a climate community, of course, we need to understand what is driving these changes, and part of this work of this paper, what was identified are changes, climate modes, and their manifestation in the surface wind stress. Essentially, the ocean is driven by the wind stress, and if the wind stress is changing, in fact, this is imposing sea level change. And what you see here is a decomposition of the changes in the wind. Basically, you see a lot of higher frequency interannual variations, partly related or resulting in ENSO. And that's sort of a mode that involves the Indian Ocean as well as the Pacific Ocean. It's a broad, big mode. But if it comes to the decadal variations, that's very nicely shown here. It's really more a basin mode in changes in the wind that is resulting or affecting the changes in sea level that we see. So basically, you have these different systems. One is a big system involving more ocean basins, changing in wind stress, but then on top you still have ocean basin modes that impact regionally sea level. So essentially then you need to start, in fact, for these longer periods, you can investigate the Indian Ocean, the Pacific, the Atlantic separately, but for the higher frequency, of course, it is a coupled, a broad system. And so how is this actually working? How is the wind impacting sea level? What you see here, first of all, is a model study. These are the observed changes in sea level for the more recent period. In fact, it's 93 through 2009. And what you see here is a very simple, a very crude model. It's essentially what we call quasi-geostrophic equations. It's a very simplified dynamics. But using this simplified model and just the observed changes in the wind, it's just the wind really that is driving these patterns, and you can start comparing this already from even this simple model, a more or less linear version. You see already a lot of agreement between what has been observed and what can be modeled. So it's very intriguing. It tells us that at least in low latitudes, once we have the wind, we seem to be able to explain a lot of the observed changes in sea level, and I will get back to this. And to indicate to you what kind of mechanism is behind this, it's in fact a wave mechanism. It's not surface waves that all of you might know, which we call gravity waves. Sort of the force driving the sea level back is really gravity. These are different waves. We call them planetary waves, where in fact the Earth's rotation and the change of the Earth's rotation with location, the Coriolis parameter, and the change is called the beta parameter, is really the driving force in these planetary waves that typically move westward. As you can see here, these are the observed patterns in sea level at average over 12 degree to 40 degree north in the Pacific, where essentially wind changes, for instance, in the eastern Pacific, start to launch these kind of waves that then start to cross the entire basin over a year or two. And again, compared with a simple model result, again, driven by these observed changes, and just by comparing these two, you start to see again how the model is able to simulate the changes in sea level by modulating the wind stress here, launching these waves that then cross the basin. And from here you can already see while one part of the basin is going up, the other part of the basin is going down, and that already will lead to basin-wide slopes in sea level. And this works actually. This is a paper by Miller and Douglas, where this is now the Atlantic, where Miller and Douglas investigated the Atlantic. What you see here are tide gauges. One is in Portugal, and the other one is in Portland on the other side of the basin. Tide gauge data, essentially you see they track each other very well, except, and that's what you have to recall, or I need to mention, the one of them is shifted by 10 years. Meaning that, in fact, signal that is created at the eastern part of the Atlantic, it takes about 10 years to cross the Atlantic by these basin modes, but then the east coast of the US or the other part of the basin starts to respond essentially along in consistency with these basin modes, the Rossby waves. So it's again, you basically can start to put dynamics in these changes that we observe, but you also start to see it's not a long-term trend, all what we see. There's a lot of variance on top. This is work from Zahn and Church in the Pacific again, where they started to decompose the pattern that we observed into an interannual sea level fingerprint, so it's more low latitudes, ENSO type of fingerprint, and a decadal fingerprint, which is more covering the entire basin, Pacific decadal oscillation mode, and sort of putting these two modes together, forget the middle part, we are really able to explain a lot of the observed changes in the Pacific, again indicating that climate modes are an essential part in driving the observed changes, and it's not just a mode. This is my last figure on these kind of modes. In fact, it's the Indian Ocean now. This is the observed changes in sea level going up and down according to these colors in centimeters per century. And what you see then here are boxes or even sea level where, and this is from Hahn et al. 2010, where the authors compared tide gauges or observed sea level changes with model results that have been driven by wind changes, mostly wind changes. And as before, you basically see that also the Indian Ocean is responding in a very intriguing way to these wind changes. And of course, one of the questions is, where do these wind changes come from? The authors actually have decomposed the atmosphere into the Hadley and Walker circulation changes. They pinpointed to a large extent these changes to, in fact, a warming eastern Indian Ocean, which has an impact on the wind. We do know this, that in the low latitudes there's a very strong coupling between SST and wind changes. And so we are able now to put together a dynamical system of why we see the observed changes in sea level and where the forcing comes from in the atmosphere. What still needs to be investigated is this warming, in fact, an anthropogenic signal or just a natural signal? And of course, the next step would be if that is already anthropogenic or not, but if in the future that part of the world gets warmer and warmer, is in fact these changes that we see in the Indian Ocean and relevant respective ones in other parts like the Pacific, are our climate modes getting into a more static part of the oscillations, and then with new oscillations on top of what might become a new mean? We really have to understand if the whole climate system is shifting into a different situation that before was part of an oscillation. This is, again, our concluding this part, a study by Schwarzkopf and Böning, where basically they also looked into the eastern Indian Ocean and basically concluded that that part of the Indian Ocean at least is affected by wind changes in the Pacific. We call this the island rule, but essentially the wind stress is leading to oscillations around Australia. And this shows very nicely, this is the altimeter observed period and an increase in sea level. But if you take a model and you simulate the full time series, there was a substantial decline before. So if you would just take this one, you would conclude, okay, we have a serious increase. But essentially the model result might in fact indicate, well, before we had a substantial decline. And so once we started with the altimeter, we might have set in a very low situation in some parts of the world, and we should not just conclude all this is just human-made, anthropogenic climate change increase. In fact, there is this longer-term oscillation on top that we have to consider. And this longer-term oscillations is indicated here. These are very long climate model runs over 1,000 years. And this is the Arctic oscillation, and this is the Southern Ocean in over some averages. This is 800 and essentially 4,000, and so this is about 3,000 years. There is no anthropogenic forcing. All you see here is just natural variability in meters. So essentially these are 10 centimeters natural variability at any time in the climate system. And so even if we start, or we believe whatever happened before 1860, before the Industrial Revolution, the system has a lot of these oscillations on top, and some of these increases that we see today are in fact much longer periods than what we have thought about before. So the last minutes I will come just projections, and I will not go very deep into this, but indicating that whatever we observed in the past, that the dynamical component in the system will continue. This is a global sea level increase estimated as part of the last IPCC assessment, on top of so-called semi-empirical models, where basically a correlation analysis has been done between global temperature and the whole climate system, if you want so. So essentially you see a substantial increase. Let's just look into what happens or what comes out of the more recent coupled climate models, the CMAP5 results. This is just the ocean part. This does not include ice. This does not include any terrestrial rebound or changes in geoid. It's just the dynamical ocean part. For a very moderate, it is a 4.5 RCP, a very moderate climate forcing in meters. So essentially some parts of the world will go up by 30 centimeters and more. Others will in fact stay fairly close to where they are today. So essentially this is just the dynamic part of the ocean, showing the redistribution of heat, the extra heat coming in, the extra fresh water coming in, to some extent at least, but also the changes of the wind leading to these patterns. And if you now look into 2, this is the one I just showed you. This is a stronger one. Maybe it's high-end. I personally believe it's not high-end really. It might in fact be the trajectory the climate system is going. You start to see some regions that are 40 and more centimeters, just the dynamical part, and again others that stay fairly close to where we are. And of course, we need to understand now the uncertainty of this and other parts. Maybe I have to rush, I guess, or I still have time. So maybe one point to mention, I showed you already the variability from the climate models and the spread to some extent, how different climate models this is in fact the standard deviation of all the 21 climate models that we use to estimate this mean over 21 climate models. You see that the models disagree in some regions substantially. And of course, this figure here, in fact, if I go back and forth, you might see that there are patterns like this one here, these ones, that appear in this figure here again, except this is from only one model. The only difference from this one model is that it has been initialized by slightly different, small differences in initial states. So that indicates to you again, and it's from 100-year forecast, that even over these 100 years and longer, the initial conditions from where we start the climate system have a substantial impact. And I conclude, in fact, from this that some of this spread might, in fact, sitting not just in the difference of the climate models, but also in the difference of the initial conditions these individual climate models used. So I think in terms of the climate modeling community, we have to go backwards, we have to take a step backwards and really understand that, in fact, essentially what we call projections, where the initial conditions didn't matter so much, it's essentially the external forcing, the CO2 forcing that drives these changes. These kind of projections still depend on the initial conditions, I believe, and we have to go back and better understand this. What else is missing? Climate models, very briefly, ice sheet dynamics. There's no ice sheet dynamics in climate models at all, and so all the mass loss from ice sheets we basically have to put in right now on top, in addition, offline, we call this, into these climate models. And I think we really need to get this fresh water into the model. We now have the very first runs where we did this, where basically we added into the climate models this fresh water, and we see a substantial order, 30%, 50% changes in regional pattern of sea level, indicating that the ocean dynamics are responding substantial to this fresh water. that's called, indicated here by this dynamical ocean adjustment to the welt motor. We do compute surface pressure in these models. Unfortunately, many of these surface pressure computations does not include the moisture part. And Anny already indicated that on global average, the moisture does have an impact on global sea level, on regional pattern as well, and we really need to correct for this. Land hydrology is not included at all, and so these are patterns that will emerge, and you will hear about this later. And of course, uncertainty, they're not missing, I mean, they are there, except that we don't understand them in the projections. And very briefly, this is in fact how the ocean does look if you start to put in fresh water around in one place, like here around Greenland. First of all, there is a fairly rapid, it's not instantaneous, but over just a few weeks global response, which in fact is not just a flat ocean, it has a pattern, but it's fairly rapid. And then this is the so-called bioclinic, it's a density-driven response shown here, basically where you basically see these kind of a planetary wave pattern, where this is a wave propagating down to the equator, crossing the equator, propagating north poleward again at the other side of the basin, and then from there filling the Indian Ocean and then leaking into the Pacific. And so these are very long timescales adjustment of the ocean on top of faster adjustment, and we really have to understand them all. I jump over the coupled system and come to the conclusion. I think one of the things we have to consider is that there is a regional pattern in sea level. If it comes to the impact on society, it's really and security, it's really the regional pattern we have to understand. In the past, I think it's true that many of the changes we observed, at least over the last 50 to 100 years, are thermally driven, but in particular over the last 10 years, we do see an increasing contribution from melting ice masses. I shouldn't say melting, because some of them might be just carving in other processes, how the ice sheets might lose a mass. That has an impact on the dynamics, that has an impact on fingerprint, sort of regional pattern on sea level, that has an impact on global sea level. And I think understanding that part will be really important. I think on the global scale and even on regional scale, the longer the time scales are, the more the heat input, the extra heat that is coming into the system will become important, but we don't understand yet where this heat is actually entering and where it's showing up. So it's not the same thing. The heat will, get into the ocean, but it will get redistributed and in fact lead to sea level rise, probably in a different place from where you put it in. The uncertainties I mentioned already, uncertainties, just to go back, reconstructions, I mentioned already reconstructions. What I show you here are in fact 4 reconstructions we have. In fact, we have more than that, but just 4. Specker et al. I showed you before. This is Church and White 2011. This is Mysanak and Cazenave 2012. This one is only model-based. So these are essentially statistically, this is taking an ocean circulation model, constrained by observations. And just by eyeballing, you basically see there is substantial spread in these reconstructions, indicating to you we have to go back, and even the last 50 years, where we think, okay, that's the recent years, it's observed. It's really not observed. It's only the altimeter period that has been observed. Everything else is reconstructed from a limited amount of information we have. And even the last 50 years we have to keep working on. And maybe I just leave the open issues here. I can go through. So let's comment. Presently, basically we start basin by basin. What are the contributions from climate modes? I have shown you this in the Pacific, where we decompose the variability into 2 patterns. I think we still have to come up with the entire budget. How much of regional variability is due to what kind of climate mode? And of course, the if it comes to the future, I think this process will not change, but the modes might change. And of course, the models, the climate models that we use to study the future might have somewhat different climate modes. We do know that some of the coupled climate models have a very strange ENSO, which is one of our biggest climate modes, but they have maybe just a very regular ENSO beat without any interannual changes of that, maybe a wrong phasing. And so it's not just the question how much of present-day variability is due to climate modes or to which climate modes, but also how is this represented in the climate model. It means to some extent how good are our climate models in representing these variations. And of course, if it comes to a CO2 forcing or climate change at all, we don't understand how this whole system is changing in its oscillation pattern and also as a trend. That's indicated here. I think the wind changes are today and in the future will have a huge impact on what we see in at least the dynamical part of sea level change, also in the longer term. Because the wind changes are changing the circulation, the changes in circulation are redistributing heat, and so a lot of what we see today in heat change and thermospheric contribution is really a redistribution of heat. It's not the heat that went into the Western Pacific that shows up, it's the heat that's being distributed by the changes of the circulation that shows up there. And so this will continue, but we have to understand how this works and how the wind is changing in the future and how the circulation is changing in the future on higher frequency. Of course, if you want to understand in particular regionally and coast smaller scales, the existing climate models are okay, they're a first step, but in order to understand the ocean, we have to really downscale. We have to get to a much higher resolution, either globally or on a basin scale, or even regionally. You have to get to a very high resolution where even the shelf dynamics, the wave dynamics at the coast is being represented properly. And I think only then we can conclude what the dynamics are today and in the future in sea level change. Thank you very much.